Hi everybody, today we're going to talk about quantum numbers. One way to look at quantum numbers is to kind of visualize them as the address of an electron. And just like your address goes from extremely unspecific, like you live in a country, let's say you live in Canada, and then you live in a province. You can get even more specific and say, okay, I live in a city called Brampton. I live on a street, maybe Kennedy, and I live at a number of a house on that street. You can even get more specific, and you can say I live on a floor in that particular house, and maybe even I live in a particular room in that house. So I live maybe in the second house, and I live on a floor, and I live in a room in that floor. So quantum numbers do the exact same thing. Now to begin, we always start with, okay, so this electron is on a particular atom. So it's on an atom of beryllium or atom of magnesium. The next way that the next more specific thing that it gets is the electron is in a particular shell. And that uses the principal quantum number. Now, we learned about the principal quantum number from Bohr-Rutherford diagrams, so it really shouldn't be anything new. And it's not that the Bohr-Rutherford diagrams aren't useful, they just need more to them to account for where all the electrons are and how it works and the shapes of the orbitals and all that fun stuff that we've discovered since then. So we had to add on to the Bohr-Rutherford diagram and this principal quantum number. And the modern atomic theory added on to it by adding 3 more numbers to this. Now the next number that was added, again, gets more specific, and that is L. It's also called the magnetic quantum number, and this tells you what subshell the electron is in. And for a little diagram up here, right here, you can think of it as the floor that the electron is on. Okay? Now L can have any value from 0 to -1. So if n equals 1, then L can be 1 minus 1, which is, it can be 0. So when you have the first shell, it only has 1 L, and that 1 L is 0. Now, if n equals 1, your L can be 0. If n equals 2, your L can be 1 or 0. If n equals 3, your L can be 1, actually it can be 2, 1, or 0, and so on. Now these numbers for L all represent letters and shapes. So when L is 0, that's the S subshell, and that shape is actually looks like a ball. It's a circle. If L equals 1, then the shape is a P, and that's like a dumbbell. If L equals 2, then the letter is D, and yeah, I'm never going to be able to draw that. And if L equals 3, you have an F subshell, and there's even less of a chance of me drawing that. All right, so the third quantum number is the ML. And this one tells us what orbital our electron is in. Now, the ml can be any value from -L to +L. So let me show you what I mean. So if L equals 0, then ml can only be -1. What am I saying? ml can only be 0. So that's one option. And when you draw that, you draw one box, or one orbital. If L equals 1, then your ml can be -1, 0, or +1. So that's three options. So when you draw those subshells, or that subshell, it's going to have three orbitals. Each of these orbitals is going to have a number associated with it. So by convention, we say the left one is -1, 0, and then +1. Now, if L is 2, then ml can equal -2, -1, 0, +1, and +2. That's 5 options, which means there's going to be 5 orbitals, and that's why we draw 5 boxes, and so on and so forth. We'll do the last one as well. So if L equals 3, then your ml can be -3, -2, -1, 0, +1, +2, and +3. So that's 7 options, which means your box is going to have 7 boxes, or 7 orbitals. And just in case you've forgotten or aren't quite sure on this, these boxes are going to be labeled, again, starting from the smallest number to the biggest number. Now, Pauli's exclusion principle states that when you fill those boxes up, you can't put, let's try this again. Pauli's exclusion principle says that no 2 electrons in the same atom can have the same 4 quantum numbers. So if this was the 1s box, and you had 2 electrons in it, because every orbital can have 2 electrons, you have to put one with a positive spin and one with a negative spin, because if they had both the same spins, they would have the same 4 quantum numbers. Their n would be 1, their p would be 0, their ml would be 0. So because those 3 numbers are the same, you have to change the 4th quantum number, and that's where the spin comes from. So for that first electron here, it's going to have a ms of +0.5. And for the second electron, that one's going to have a spin of -0.5. So by convention, if it goes up, it's a +0.5, and if it goes down, it's a -0.5. So they have 3 quantum numbers that are the same and 1 that is different. Sorry about that. Now, the last thing we want to talk about is when we're filling those boxes up, we have to follow a couple rules. The first one is the Aufbau rule, and that's where you draw that diagonal, and that means that you have to fill the lowest energy level first. So you're going to follow that diagonal rule to do that. The second rule is Hund's rule, and Hund's rule is talking about filling up those orbitals. And basically what it says is when you're filling up some boxes, you have to put a single electron into each orbital first before you can double anything up. Not only that, but each of those single electrons have to have the same spin. So they all have to be going up or they all have to be going down. And we're going to do up first by convention. Once you've done that, then you can fill or double up those orbitals. That means that when you're doing or filling up your boxes, you're going to put this one first, this one second, this one third, this one fourth, this one fifth, and this one sixth. And that's Hund's rule. So hopefully this has been useful. Have a great day.